Okay, so as I'm sure everybody knows, the ocean controls how fast the Earth warms from global warming. If you didn't know that, now you do. And this is work that I've done with my grad student, Yemi Garuba, of course, which means that she actually did the work. Here's my advertisement for the department in our programs. That's good enough. The thing that we've seen about global warming is that when we model it with climate models, we can increase the amount of CO2 and see how the model responds in terms of global mean temperature, like in this graph. And in experiments, when we actually stop raising the CO2, say at year 2000, we see that the models show still warming after that. And you can see from these two curves, different models actually predict different amounts of warming. And the reason for that is that the ocean provides what people call a thermal inertia to climate change. So to picture what's going on, think before global warming, you have a state that the heat flux into the ocean, represented by that box down at the bottom, is equal to the heat flux out. And when you add greenhouse gases, the effect is to put more heat into the ocean. And now there's an imbalance because the flux, at first, the flux from the ocean going out is too small, and so that extra heat goes into the ocean warms up, and there's a physical law that when something warms up, it radiates more, so the ocean will now emit more, and it keeps getting warmer and warmer till we reach a new balance where we have an equilibrium where the Earth is warm. That same kind of process takes place in the atmosphere as well, but the ocean absorbs a lot more heat for a given amount of temperature change in the atmosphere. So most of the heat is actually going into the ocean, and how much heat goes into the ocean depends on how thick the layer of ocean is. And so depending on how much heat the ocean absorbs, it could be that the warming we've had represents all the warming we're going to get from the last 100 years, say, of CO2 emissions, or it could be that's only a small fraction and we have much more in store. And so figuring out what's going to happen, we need to know what the ocean's role is in that. So, okay, now my next half of my talk. So the ocean is actually 5 kilometers deep, and so there's a big question of how much of that 5 kilometers is actually engaged by this warming. And you can see in another experiment where the CO2 is increased abruptly. This is a cross-section of the ocean, depth and latitude. You can see that at first the heat is just in the top few hundred meters, and then it sinks down, and you can see that it's different amounts in different oceans. And the work that Yemi and I are doing now is to try to figure out how that water gets down. So for instance, and there's a lot of different mechanisms, just to show one, you see that in the North Atlantic, when we put a tracer that represents the extra heat, we see that it actually only goes down to a depth of, say, 500 meters in very small regions. And then if you look over time, what's happening is it seems to be spreading out from that region, and actually the ocean currents in that part of the world are going in about the same direction that you're seeing by the tracer. So ultimately what we'd like to be able to do is relate things we know about the ocean, like the circulation, to things we want to know, like how the circulation carries the heat down. And once we do, if we understand the mechanism of heat uptake, hopefully we'll better understand which models are doing a better job at showing how much warmer the Earth is getting, and finally help make projections of what the future holds. Thanks.